Welcome to the day 4 of the machine learning short course. So last day we ended with the concept of a very brief concept of clustering, and today we are going to start the concept of artificial neural network. So how it works and each and every detail of this ANN we will see very shortly. So we will start with the need of artificial neural network with a very simple task, that recognizing a person. That's a very common task for an human being. Now question is that if the computer is given to, this same problem is given to a computer to solve it. Now what are the steps a computer can follow? I mean, we can have a step something like this. Like we can have, suppose that there are a lot of images stored in a computer. Maybe 1,000 or 10,000 doesn't. Some, large amount of images, and the one of the image of the person will be given to the computer. Okay. Now the computer will basically check that image characteristic with respect to some data uh, from the database, and then the finally among all those 100 or 1,000 or 10,000 images, the images that actually shows closest with the image of the person will recognize the person as something like that one, right? So it can be something like this, right? Till now, in case of searching, the different techniques that we have seen will, maybe it can, it can, obviously the computer will follow something like this, right? So all the searching techniques that we have seen, at least till now. Now question is that what is the time? Ultimately time is very important thing. So what is the time taken to give this output? Now obviously in a worst case scenario, it can be hours or days for a fastest computer. The reason is that there are maybe lakhs of images, right? So in a practical scenario, that there are crores of people, and among that crores of people, if you want to find only one people by this type of searching, each and every time, a particular image will be searched with all the images. So pretty, it will take pretty time, right? But now, in an interesting question is that what is the time taken by us and a normal people? Suppose you have previously known the person, or maybe you had some idea. Now, how much time will be taken by you? And surprisingly, it is couple of seconds, right? It is couple of seconds. So, there are very huge difference between these two. If I use the approach of uh, searching a image through a computer, and if I do the same thing by a human being, we have an hell and heaven difference with respect to the time. But you see, if you check the difference between the traditional, the speed of a traditional IC or a human brain, we will see that traditional IC speed is very faster than us, because we all know that computer operated in nanosecond, or maybe more less than that, maybe picosecond, and human brain speed is in microsecond, not more than that. So still, you know we can see that recognizing a person, this task is taken actually very short time than a computer by us, right? So, question is this: that although the human brain speed is 6 order times slower than present IC speed, but the human brain is much faster than computer. Now, what is the reason behind this? Because we all know that computer is very faster. Should be, because it's 10 to the power 9, and we are in 10 to the power, sorry, 10 to the minus 9, and we are in 10 to the minus 3. So computer should be faster, but still it is not happening in this situation. Why? The reason is that the structural component that we consider as a neuron that we have in our brain are massively parallel. So we actually have a parallel computation for doing the same recognition task. And you see, in a general estimate, we have 10 billions of neurons in our brain, in a developed brain, and their interconnections are 60 trillion. So it's a very huge parallel task can be possible. And that is a key reason because we are faster for doing the recognition type of task. If you compare with a task for addition of two numbers or some mathematical task, maybe you will see that computer is very faster than us. But recognition task is a different thing because for recognizing a particular picture or a particular person is not a simple value. A person is actually defined with respect to various features. Like the concept of feature already we have. So with respect to various features, how the what is the uh, way by which this task is, the recognition task actually done is going to be very complex. It's not to be so simple. And that is a reason where these massive parallel operations come into play. And that is the reason why we are faster than computer in this situation. Now question is that obviously if I want that computer will do the same thing on behalf of me, then there is only one way, that we have to make the computer faster. But you cannot do faster with respect to the processing speed only. You cannot do that because ultimately if it follows a similar type of logic, then still this computer will remain slower than a human being. So that means somehow it will be better if we are able to incorporate the strategy that is happening in our brain to a computer. And from that point of view, the concept of artificial neural network came. Why it is artificial? Because this is a concept what we implement in a algorithmic form. In our brain we have neural network, in a computer we have artificial neural network. So this artificial word is added just because that really neural network doesn't possible to exist in a computer. We are mathematically, we will actually define this neural network, and then everything, the algorithm, the approach that we will design, everything is artificial, right? So let's go to the concept first. The usefulness and capabilities of this artificial neural network. So the first is thus non-linearity. The non-linearity in the sense that in any situation, in most real world problems are non-linear. That maybe considering like considering putting a curve with a lot of data points, or maybe recognizing a person, or maybe anything, it's not so linear. Like you cannot define something like a unitary method that if this is happen for this person, then this will happen for that person. So person to person feature varies. You cannot relate two features in a linear equation. So that's why most of the problems is non-linear. And this artificial neural network is highly efficient to capture this non-linear behavior, so that the whole system can act as just like what human brain does. The second point is that input output mapping. Here we have a concept of learning with teacher. So this concept learning with teacher already we have seen in case of supervised learning. So that means one thing is clear, that the learning strategy that our artificial neural network possesses is supervised learning. So every time we have something at the output, we have some desired output, and we will get some output from the neural network. Depends on the error. Somehow what we can do, we can actually adjust those free parameters that represents the artificial neural network, so that ultimately the whole neural network can be learned for the future inputs. And same thing happens for us also. I mean, if I consider the neural network for real neural network in our brain, so we have some teacher every time when we were child, and actually initially when a baby actually comes in the world, she doesn't have any it doesn't have any learning. So the neurons present in his or her brain is basically, is just initial, the free parameters present in the neurons are just initialized by some arbitrary value. You can imagine in this way. And then as soon as it gets information from outside world, maybe from its parent or maybe someone else, day by day the default the those free parameters of the neuron gets updated, so that, for example, after some time, the baby can recognize its mother, its father, and many other persons. Like similar thing happens for here also. So we have a learning with a teacher concept in case of artificial neural network. The third point is that adaptivity. So this is actually just we are discussing that adapt the free parameters to change the surrounding environment. What does it mean? If the environment changes, okay, then the free parameters will likely to be changed. For example, suppose that you are in say month of March or maybe April, which is very hot. At that time, whatever to wear you will realize is not same as month of December or January, which is winter. So as the environment change, your free parameters of your neuron will basically change, so that it can actually judge correctly what to do and what not to do, something like that. You can think in this way. The fourth one is that evidential response. So evidential response is actually nothing but just a decision with confident measure. So if you have artificial neural network, if you want to show that it's responding correctly, we have some confidential measure confidence measure, so that we can say that okay, this neural network is working fine for the various number of inputs. And what are the confidence measures that we have already seen? That maybe F1 score, maybe confusion matrix, maybe mean square error, and many more. So it depends upon which type of problem it is, and uh, it can actually adjust, it can be adjusted over there. Now, the fourth one is the fault tolerance. That is, failure of a very few neuron or collection or connections should not collapse the whole system. So, this interesting feature we have present in our brain also. Like there is feature in our brain is that if some part of the brain is not started, suddenly stopped working, then the entire responsibility of that part is actually distributed through the other part of the brain. So that means damaging a very small part of a brain does not mean that whatever you are doing the task with that particular part will get vanished. That will get distributed through the other part of the brain, and this is what we call fault tolerance. And same thing is happen in case of artificial neural network also. Like this is the very interesting and important property of an artificial neural network. And last one is that VLSI implementability, because ultimately, since it is an artificial neural network, ultimately you will, if you want to use in real life, then somehow you have to implement this particular um, concept with respect to some with respect to some electronic chip so that everyone can use that. So the concept of artificial neural network is can be possible to implement in case of electronic chip. That is the very interesting point for uh, I mean for uh, for the as an usefulness of ANN. Anyway, so let's move forward. You see, now here a very last point, which is very interesting point, will come. That is neurobiological analogy. What does it mean? That the image that you can see on the top left corner is actual image of a neuron, of a neuron of a brain. You see, there are three parts of this neuron. One part is called dendrite, and another part is called cell body, and another part is called axon. What this dendrite is, these dendrites are actually take information from the outside, and within the cell body those information is processed, and the output of the information is carried forward through this axon to the another neuron. So here in the in the diagram, it actually shown two neurons, how they are connected with each other. So if you just draw a corresponding diagram with this particular actual neuron, it looks something like this, what you can see in image B, that is in the bottom left corner, that we have some inputs which are actually dendrites, and the cell body that we call soma is given in a something like in this red circle. And so this particular circle actually does something, actually accumulate all the information coming from different dendrites, and then that information is transferred through the axon. And there are many other neurons, or there are many other dendrites of another neuron connected with this particular axon, something like this one, which basically will take the information from one neuron, previous neuron to the next neuron, right? And depends on this concept, depends on this scenario. There were actually two scientists who designed a mathematical model of a neural network, that is what we call artificial neural network. That model is called Maculo-Pitts model. So if you closely watch this Maculo-Pitts model, sorry, if you closely watch this Maculo-Pitts model, you will see that the by characteristic, we have a very interesting similarity we have with respect to these both images with this one, right? With this one. So you see the dendrites that we are considering over here, or maybe somewhere over here, is nothing but this x1, x2, x3, x4, or you can assume that there are four informations which is coming from the other neurons, maybe through the dendrite, and they are actually connected with this soma that is presented over here, something like this. Okay, now question is that, always remember one thing, connection obviously there, but you know there are maybe, it happens that in general original scenario also it happens that if a neuron is connected with several other neurons in some special scenario, maybe for some special task, some particular task, all the neurons doesn't have the same impact to the next neuron. A neuron can take, maybe some of the neuron has some particular impact, some of the other neuron have some other impact. So now question is that which neuron has greater impact and which neuron has lesser impact, how you will express that. That impact is expressed what we call synaptic weight. Okay, so each and every connection has some weight. Mathematically, when we design a neural network, each and every connection has a weight, and that weight actually will determine that how much impact of that particular dendrite or will have to that particular neuron. So here we can see that we have 4 different dendrites, and even including this bias also. Now what is bias, that I am coming very soon. This bias also is one type of, you can assume one type of dendrite. Okay, so this dendrite has the synaptic weight written as BK, and other synaptic weights written as W with respect to which particular dendrite it is coming. Since it is coming from x1, it is written WK1. Since it is coming from x2, that's why this weight is written as WK2 in this way. And what happened over here? Here, mathematically what is done, we have a very simple addition of the multiplications. Addition of the multiplication in the sense, the x1 will be multiplied with WK1. Similarly, x2 will be multiplied with WK2, x3 will be multiplied with WK3. So, and these multiplications are added. Something like this. You can see over here. This given. Right. Now, still, up to this one, we have, you will say still this is linear. Right. We have a simple multiplication. There is no nonlinear term. Okay. Now, this bias will play a vital role over here, and it's given that bias actually starts introducing this nonlinearity. Not only for this bias, actually bias also connect with the similar way in a linear fashion, but the nonlinearity actually comes because of this what we call activation function. What does it mean? It means that whatever the summation result, that is UK, present over here. So basically one thing is sure, that UK, maybe I have not written this one. Let's write it. Actually, this is what you can assume as UK. Okay, so UK is this one, the addition of all these multiplications, and this UK actually just a minute. Oh, I'm sorry. Just a minute. There is a mistake over here. I have by mistake I have written vi equal to ui plus vi. It should be actually vi equal to, I'm sorry, yes, vi equal to ui plus, actually it should be written as bi. So this summation is considered as UK. So this UK and BI into bias will be considered as this VI, and this VI is the input to this activation function. So if we have an activation function, this VI is the input, or maybe VK, whatever you can consider, and the YI is the output. So generally we express the activation function by this symbol phi. Okay, so that mean in the McKillop-Pitts model, actually what it says, that it will basically says the how the interconnection of the uh, of the neurons will happen. Now always you see a very interesting thing, that whatever we are considering over here x1 as in dendrite, maybe this x1 is an output of another neuron, right? So that means, if I consider this is one neuron, and maybe this will be connected with another neuron in the next stage. So in this way we can have multiple stages of the connection. We can design, depends on our, depends on our requirement. Okay. So in a in a nutshell, in a very basic form, a simple neuron can be mathematically modeled using this McEuroe-Pitts model. So basically the artificial neural network that we will prepare, or every uh, advancement of the artificial neural network that we will see based on this McEuroe-Pitts model. Okay, now let's see what are the different type of activation function possible. So you see, we have three activation functions over here. The first one, the leftmost one, is the threshold function. What does it mean? That it means that the threshold function have a particular criteria, that if this vi is what? Vi is the summation of the bias into its synaptic weight plus the wixi, right? So you can see over here wixi actually. So you see it's wixi. I'm sorry, I should not. Maybe you can see it is given that xi xj into wij, but I am not going to write in exact, I'm not going to say in exact details. Just as a, you can assume that wixi means, you can consider that x1 as, the synaptic weight associated with x1 is w1, right? Synaptic weight associated with x2 is w2. Synaptic weight associated with x3 is w3. According to that, it will be wixi. So so this addition of wixi is actually this uk, and this bias into its synaptic weight is, if you just add them, it will become vi. So that's why you see in the criteria it is given, if vi greater than equal to 0, then the yi, that is the output of the activation function, will be 1. So in case of threshold function, we have output is either 1 or 0. Okay. And vi is lesser than 0, then it's 0. That's all. So the x-axis represents what will be the summation result of the synaptic weights, addition of the synaptic weights with its corresponding input value. That is the x-axis represents, and y-axis represents what will be the activation function output value. That's all. Okay, and this is true for all the cases. Now in case of signum function, it is little bit different. There is no concept of 0 in case of signum function. We consider it is either +1 or -1. In case of linear function, it's really linear. That's why its name is linear. That we don't change vi. We say that if vi is greater than 0, so let's keep it vi, and if vi is lesser than 0, I will say again it's vi. So there is no change. Now question is that why this different activation function? Where we will use this different activation function? Which activation function is useful for which cases? It actually depends upon the problem. So generally in most real world problems are non-linear, so we don't use this type of hard boundary, because either 0 or 1, it's a hard boundary. I may have something in between 0 and 1. Similarly, I may have something in between +1 and -1. Right. So we try to avoid this hard boundary in a general classical nonlinear problems. So in that case, we should come for the other three type of activation functions which are very popular in artificial neural network literature. And these are called sigmoid function, tan hyperbolic function, and ReLU function. And what this sigmoid function say? This sigmoid function say it's yi equal to 1 by 1 plus e to the power minus vi. You see, this particular function is should be popular to you, should be known to you. If you are able to recall my previous classes, then you will realize that this function was present in case of logistic regression function. And we have seen there was a very interesting feature in logistic regression. I mean, in this particular sigmoid function, that is, its derivative is very interesting. Its derivative is equal to the function itself multiplied by 1 minus the function. And you see why this particular v is given. Why this particular v is given? This v is actually you can assume as a tuner. Tuner in the sense that for example, instead of having the graph something like this, the graph can be something like this also. Even the graph can be something like this also. Even the graph can be something like this also. So the graph actually that was given in this particular slide is an ideal curve where v is equal to 1. But if you tune this v with some value, maybe 0.5 or 0.75, you will see the curve is changing. Now this v is somehow, in sometimes it is important to adjust the output of this activation function, and it also depends on the problem. So in case of using these different activation functions, if you have a tuner to tune this curve, what is the best value, that is not possible to define. It is under research. So you must have some amount of trial and error method to tune these parameters. But this is not a parameter that is adjustable for the learning. We have not still ended, started the learning strategy. This is just, I'm saying, a part of the activation function, that's all. So through the ANN learning, you will not able to tune this V. This V is just for our purpose. In many cases, V remains 1. But I have told you that you have an option, you can tune this through adding this variable. Similarly, and you see a very interesting thing, that this sigmoid function actually gives a nonlinearity which contain you can say infinite number of values between 0 and 1. So like in previous cases what we had, that in case of threshold function, that either 0 or 1, this hard boundary is broken in this sigmoid function. So it can take in from 0 to 1 any value, and depends on that maybe something will work, because a particular feature, output feature, may not have a value only 0 or 1, maybe something between 0 and 1. In that case this sigmoid function will work fine. Similarly, the tan hyperbolic function do the almost same thing, but here the range is -1 to +1. So basically you can assume that signum the advancement of the signum function is tan hyperbolic. In case of signum function, we is a hard boundary, either -1 or +1. But tan hyperbolic function say that we have an infinite number of values in between -1 to +1, and that is also non-linear and depends on the problem. Obviously, you can use this tan hyperbolic function. So if the output desired output may have a negative value, which is till -1 or maybe -0.5 or -7.5, in that case sigmoid function will fail, because sigmoid function will not give you negative value. That is why tan hyperbolic function is given. And one of the most interesting and used activation function is ReLU. The full form of ReLU is rectified linear unit. And you see, this ReLU have a graph something like this. It means that ReLU actually cut this particular line from 0. Whatever negative, whatever below 0, it converts to 0, and whatever after 0, it converts to the same value. So you can say ReLU is a it's linear, depends on what is the threshold. You can assume that if the threshold is 1, from 1 I will have a linear, and before 1 I will have a simple straight line. I can have something like this. So this ReLU is mostly useful in case of deep learning cases. We will see in future that in case of deep learning where you can use this ReLU function, and you will see if you search in more about this activation functions, you will see many other activation functions. I have not included them over here just for time restriction, and there you will see there are many other advanced activation functions which are basically advancement on ReLU. For example, PRELU. What you can say PRELU? I must say it is PRELU. Okay. In case of PRELU, this line that we can see over here, just a minute. The line that you can see over here actually it's not exactly 0, it's become negative, but the linearity breaks. So in case of ReLU function, you will say it's linear from 0, but it's not linear as a whole, because for the negative values it is not in the same path, same slope. That's why it is a part of non-linear activation function. And you have this different formulation for this nonlinear activation function, so you can easily use that if you require in future. So now let's come for a practical interesting problem that you can solve in using artificial neural network. Just a minute. Okay, so what is the task? The task is that forecast the monthly sales by studying the relationship between the monthly e-commerce sale and online advertising cost. So clearly this is a linear regression problem. If you put these data points as we have seen in the left part, you can see it's clearly a linear regression problem. And you already have idea about linear regression, but you have only idea. We didn't still have not, you know, uh, discussed how we can actually implement this linear regression. And this is the point. Today we can see that we can implement this linear regression using artificial neural network. And how we can do this? You see, just forget about artificial neural network right now. If I give you this set of points, just forget about the lines even given over there. Okay. So what, and if I tell you that just put a straight line that will be the best fit on that particular line, then what you will do? Will you able to, draw that particular line, I mean, at the first attempt? It is not possible. So what basically we'll do, one thing is clear, whatever the line may be, I'm sorry, whatever the line may be, this is the formulation of a straight line, and this remains same. This remains same in the sense, whatever the line may be, we will have some M and we will have some C, and that actually define the line. So that means the line may be, arbitrarily, that means these two are what? Free parameter. Even this is also a free parameter. Now see, initially, since we don't have idea about the straight line, so what I will do, I will take an arbitrary M and C. And if we take an arbitrary M and C, obviously it will basically lead to some straight line. For example, the straight line can be something like this. Something like this. Now, if we put this straight line over there, and if we compare the difference, I mean, if we just write the straight line, I mean, no, just draw the straight line, connect this point. Okay, so straight line is something like this, and we can see that this is the error, right? This is the error. This is the error. So in this way, if you calculate the difference between actual points and the points on the straight line on that particular, for the particular x, you will get the error, and you find that this error is high. What you will do, you will try to adjust these free parameters. That means you will try to adjust this M and C so that next time this average error with all the points gets minimized. Something like, you can say that next line can be something like this. And again you will compare with all the points. And again we found that, okay, still I have some error. So let's try to adjust free parameter more. And ultimately you will get this particular straight line, which has minimum average error. Maybe in case of, whatever the M and C you consider, you start with a point, with a straight line, maybe something like this, maybe something like this. It may happen, you don't know, depends on who M and C, which straight line will occur, you don't know. So that means, if I just assume in place of you there is a computer, and computer has to solve this problem, so what computer will do, computer will basically start with this arbitrary M and C, and will try to adjust this M and C so that computer can find the best straight line that have a best average accuracy. or best minimum error, average minimum error. So this adjusting this M and C is the target of the artificial neural network. So if these are adjusted, that means we can write whatever is written over here. We can write, I'm sorry, we can write the line in this way, right? Yi equal to W11x plus W21. What is W11 and W21? This W11 is representing this M slope, and W21 is representing the intercept. C, the constant. And we can design a Maculopitz model shown something like this in the below, this one. What we have done? We have kept this x because we know for different x's we will get different y. We have kept this x and a bias plus 1, and we have considered the synaptic weight between these two are as W11 and W21, so that ultimately I will get x1 x into W21, that I require x, I'm sorry, by mistake it should be, let's correct it here. This should be W21, I think. Yes, this should be W21 and this should be W11. Okay, so I had a just mistake when I draw that. Anyway, so ultimately the goal is that we have to design this this W21 and W11 is the synaptic weight. So if you just add these two, what we have seen over there, that x into W11 plus 1 into W21, that means W21, is this u, which will be further go through this activation function. That activation may be linear function, then whatever the summation result will remain same, and I know what should be the y. I have this idea, right? For that particular x, for a particular x, what is the y that I know? And that is the desired y. And for that particular x, still when the learning has not yet started, we have a arbitrary value in our W21 and W11, just like arbitrary value in M and C. With this arbitrary value, I will get some y. Now for this particular x, I know what should be the actual y, and that is the error. So what we have over here, we have, you can draw something like, here we have a checking. Here we have y desired, and this one which will get is error. Sorry. This error will do what? Will basically adjust this synaptic weights so that for the next point I will get better y which is very close to the desired y. Now question is that this is actually, this is actually what actually learning is, and this is what happens. So if you just imagine that it's continued for a lot of different samples, so a time will come when this W21 and W11 will be learned so good that it will be very close to the actual M and C that represents the line, and at that time you will get minimum average error. And you can say your Mackey-Lopez model has been learned well so that it can represents all the points, given points, with minimum average error. And if you do that, that means after when the learning will get completed, then what you can do? You can assume this as simple black box, a simple black box. So the learned model will show a simple black box. In one side we have 1, in another side we have x, and we have an output y. That's all, right? yi, and maybe it's x. So now why? What is the purpose of this? Because maybe you want to know, you want to predict for this x what should be the y, but it's not available over here. So what you will do? You will put the value of the x over here and we will get this output yi. So this is the yi after getting this curve, and this is what I require because I need a forecast. The monthly sales by studying the relationship between the monthly e-commerce sale and online advertising cost. So this is what our goal is actually, and this is now question is that how learning is possible. Obviously, you see a very interesting thing over here, that when we had this particular data points and we want to fit this particular line, when we started from here, maybe started from here or maybe in other side, doesn't matter, we had some average error, right? Average error for what? For some particular value of W21 and for some particular value of W1. You have some error. What you are doing? You are getting the error, depends on the error. Somehow you are adjusting this W11 and W21, which are free parameters, so that next time the yi become much closer to y desired. So what will happen? That means what I'm expecting, what I'm actually doing, I'm actually optimizing the errors. I'm trying to minimizing the error between the actual output and the desired output. And depends on this, the curve of the error has been generated. You see, if you try to imagine a three-dimensional situation where in two dimension we have two different w and in y axis we have an error, this error looks something like a bowl. The surface of the bowl is the actually the value, the possible values of the error that can happen for some value of W21 and W11. Right? In this particular example, we have started from here. We have started from here. Just a minute. We have started from here. But it does not mean that always the error starts from in this direction. Maybe you can start from here also. It depends what is the value of W11 and W21, because just like what we have seen, that if we take another arbitrary value for W11 and W21, maybe I will start from in this side. So from which side the learning will start, the curve fitting will start, I don't know, because I have taken W11 and W21 as an arbitrary value. I don't know what should be the optimal value of W11 and W21. If I know the optimal value of W11 and W21, at the first attempt I will get the card. That is not possible. So I start from arbitrary. And with lot of different trials with these data points, comparing these data points with the actual output, we are trying to minimizing this error. So you see this error, the direction of this error, that's why the direction of the error is given in this way, something like this. You started from here and you come to almost zero. So it's almost zero error. And you can have in anywhere in the surface, you can start. It depends upon, it will entirely depend upon what is the value of W21 and W11. Whatever may be. But we always start from the upper part of the surface in somewhere, and we will try to slide down so that I will get almost, basically we are actually going downwards, sliding downwards, so that error has been optimized. And if the error is almost zero, that means whatever I am getting the output and whatever is desired almost same. So that means I can say the line has been fitted well on the data points. And naturally you can say that, okay, I have lot of outliers over here, lot of points which are not on the line. Yes, that's true. We are not exactly, it's not possible to fit each and every point on the line. If it happens, it will become overfitting. But what we can do, we can try to optimize that line such that average error has been minimized. Okay. Now if you see, this average error is something like this. So it's actually sum square error, right? Now one more view we have. If you consider the two-dimensional view of this whole scenario, you see for some particular set of weights, your cost was something like this. You were, due to your initial weight, you were over here, your error, and you will slide down to the almost zero error that we have seen in this three-dimensional view. Now when you are in this particular point, you are on this surface, you see what is the gradient of this surface. The gradient is actually towards above, right, in this direction. So your gradient is towards above and you are sliding down actually, against the gradient, right? So that is the reason the algorithm that we will use to optimize this error is called gradient descent algorithm. And this is the reason. Okay. So we will start with this gradient descent algorithm in the next class. Very soon, maybe within a couple of days. And then we have to continue with the other learning part of the neural network. Thank you.